Hi everyone, welcome to lecture 17. This is the third part of the shape selection series, and we are still in module number 3. The road so far. We have built off from strength of materials classes and looks like we have got things related to shape efficiency factors that allow us to understand how mass can be minimized or cost can be minimized in a design that not only depends upon the material but also the shape. So these could be stiffness limited designs that we looked at, strength limited designs, and they are useful in this particular case in bending loading. And we've seen some examples in the design exercise in the previous class on torsional loading as well. So all this was with the perspective of methods that could be in the form of a design platform, a digital tool that allows us to make simultaneous choices between material options and shape options that best translate a design into practice. We also looked at the fact that knowing the material properties of modulus and yield strength, you can estimate what is the upper limit for a shape factor. And for example, for these four materials, we can see that using this equation over here allows you to get to these numbers. Remember that E is in gigapascals and sigma is in megapascals to be able to get these types of numbers. The numbers in the brackets, however, are experimentally measured numbers, and in terms of what is the theoretical limit. Pause to think, how would you measure this experimentally? And in the next design exercise, we will look at ways to be able to do that from very tiny shapes involving shells and bone structures, so microscopic shapes, to macroscopic shapes such as bridges of different kinds made from different materials. So the two numbers that you saw over here, one is the theoretical limit based on this expression using the right units, and this is the empirical maximum. The shape index itself is a dimensionless term. So far, so good. And so while that was phi sub e, so the stiffness limited design in bending, understanding how mass can be minimized and how shape can be effective, most effective in minimizing mass for any given material. So similarly, you can also have a number of different values for strength limited designs given by phi sub f. And as a rule of thumb, this maximum phi sub f again indicates the limit to which you can improve the shape efficiency for any given material. It depends again on material properties, and at some point you will have buckling occurring before bending failure, and so that is why you have upper limits. All materials have upper limits in material properties. That's what we are trying to establish over here. This maximum phi f is proportional to the maximum phi e to the power half. So square root of this roughly. Now if you look at this, square root of 65 is roughly 8 point something. And so it's not exactly the same. Square root of 8 is about 3. If you plot square root of phi e as one way to estimate these numbers, and phi f that is actually reported, which is right, so square root of the first column term plotted against this term, it turns out to be a straight line, so with an r square over 99.7. So that means there's a very good correlation between these two terms. It is just off by a couple of factors in terms of the intercept and the slope, but otherwise this proportionality is quite valid. We went ahead and then used this in the CES EduPack with these Ashby bubble charts. Here modulus versus density is provided with appropriate units, and you see that there are families of materials, foams over here, natural materials over here, elastomers over here, polymers over here, composites, ceramics, and metals, all clustering in certain regions. And we saw how to be able to get a selection line of a suitable slope that depends upon the loading condition and the material index thereof, and allows us to filter off options and down select certain options that satisfy design criteria.